So David, can we start?
Yeah, sure.
Okay, so hello everyone and welcome to today's edition of our extreme and probabilistic combinatorics webinar. Before we start with our today's speaker, let me quickly go through the technical stuff. So this talk is currently being recorded, so please bear that in mind in case you want to ask questions. What we usually do at the end, after the talk, there is a recorded part, and then we switch off the recording in case anyone wants to ask any further question or want to have an informal discussion. During the talk, if you want to ask a question, please just unmute yourself and go ahead. If you have a problem with your audio, as an alternative, you can write it in the chat and I can read it out to our speaker. And yeah, I think that's it. So now it's my great pleasure to introduce David Ellis from Bristol, who will talk about the union closed conjecture. So David, please.
Okay, well, thanks very much for the invitation. It's a great pleasure to talk in this very nice seminar series. Yeah, I'm going to be talking a little bit about the union closed conjecture. Not solving it, of course, because otherwise you would have probably heard about that if that had happened. We've been looking at the transitive case of the union closed conjecture, which is quite a nice special case. Everything I'm going to say is joint with James Aaronson from Oxford and Imre Leader from Cambridge. So as many of you probably all know, the union closed conjecture is probably one of the most famous open problems in extremal combinatorics. It's kind of a folklore conjecture from the 70s, but certainly it was thought of by Peter Frankl and a lot of other leading figures in extremal combinatorics. At roughly the same time, so it's often known as Frankel's union closed conjecture. And as you probably all know, it says that if n is some positive integer, and we have a family f of subsets of 1 up to n, which is closed under taking unions, meaning that if A and B are both an F, then their union is also an F. And furthermore, we have this non-triviality condition that F isn't just the union closed finally consisting of the empty set. Then there exists some elements of the ground set such that at least half the sets in F contain I. So it's a very appealing statement, and despite lots of combinatorialist best efforts over the last 40 or so years, nobody's managed to solve it yet. There are some quite nice partial results on it, although no absolutely groundbreaking partial results, I think it's fair to say. One of the nicest results maybe of the last 20 years was a result of Baller, Bolobash and Eccles from 2012, and that was that was recently improved slightly, but I'll state what their theorem was. So Bass and Eccles proved it for union-closed families with measure at least 2/3, if you like, under the uniform measure on the power set of 1 up to n. I'll abbreviate union-closed conjecture to UCC in what follows. So they proved it for rather large families, large as a fraction of the size of the power set of n, and that was recently improved to families of measure at least a half. In fact, a tiny bit stronger than that. That was a theorem of Ilan Karpus from 2017 that actually holds for union-closed families. With f at least a half minus a very small explicit absolute constant c. And the proof is nice. It uses basic Fourier analysis on the Abelian cube. At least to get the half, I would c equals 0. It uses basic Fourier analysis. To get it with a half minus c, where c is a very small absolute positive constant, he has to use some slightly more technical Fourier analytic machinery. For example, theorem of Kindler and Saffer about sort of characterizing the Abelian functions whose Fourier transform is mainly concentrated on the lower frequencies. So to get the c, you have to be quite clever. But to get the half, well, it's still a very nice proof, but it's a short proof, very short and elegant, using sort of some nice facts about Fourier analysis on the Abelian cube. So it's worth looking at that paper for sure. And last of all, maybe in terms of prior results, I'll mention a result of David Reimer from a bit earlier, actually. So I want to keep those two theorems up, so I'm going to have to do something slightly suboptimal, but rubbing this off. This is the theorem of David Reimer from 2003. That if f is union enclosed and non-empty, and also non-trivial. And again, it's a subset of the power set of 1 up to n. Then the average size of a set in F, which is of course this, is at least a half of log(n) to the base 2 of the size of the family. Why is that interesting? Well, I mean, it's obviously an interesting statement in its own right, at least I think it is. But for any element of the ground set, it's natural when one is studying the union-closed conjecture to find the abundance of that element to be the fraction of all the sets in the union-closed family that contain that element I. And then the union-closed conjecture can simply be rephrased by saying that there's some element of the ground set with abundance at least a half. So, so let's define that. And it's always defined with respect to a fixed union-closed family, of course. And as I've said, simply number of sets in the family containing I divided by the number of sets in the family. So, of course, the union-closed conjecture is equivalent to saying that there's some element of abundance at least a half. And the natural, very first thing to try when you first hear about the union-closed conjecture is you think, well, maybe it might be true. Maybe it might be true that the abundance of a uniform random element of the ground set is at least a half. Now, I might call that a silly conjecture because it's very, very easy to show that that's false. I'm going to rule out silly trivial cases. So is it true that the average abundance of an element is at least a half? Now that average abundance, it's pretty easy to see that this is equal to 1 over n times the average size of a set in F. i.e. the average fractional size of a Saturn F. So we're saying, is it true that the average size of a set in a union enclosed family is at least n over 2? And of course it's not, because well, you can just take some small chain or something, and then just artificially enlarge the size of the ground set by adding in a load of elements to the ground set, and then just well, it's clearly false. There are lots of ways of wrapping it, but I'll just give one example, which is maybe the first thing one might write down there. It's quite when you first start thinking about the union enclosed conjecture, it's quite natural to consider chains. So this is okay. So this is a silly conjecture. It's false, but Reimer's theorem gives something weaker than that for the average abundance of an element, but still interesting. So so Reimer, what does Reimer imply? Well, the average abundance is at least a half of not sure that. Okay. And that actually implies the union enclosed conjecture up to some constant, where in the case where the family has size 2 to the omega of n, so it's actually quite nice. This can be seen as a weak version of the silly conjecture. Okay. So what we've been focusing on is the transitive case of the union enclosed conjecture, i.e., where the union enclosed family F is not only union enclosed, but also its automorphism group act transitively on the ground set. So obviously, for the special case of transitive symmetric union enclosed families, the silly conjecture.
Sorry, David, can you repeat?
Yes, sorry. Did someone?
Could you just repeat the conjecture once again? Like just there are many things written, so I'm a bit lost.
Sorry, could you speak up a bit or turn up your volume?
I was just asking, could you reiterate Seeley's conjecture?
Sorry, I still can't hear. Asking to give a what? Can anyone else work out what that question was? And maybe repeat it. Yeah, maybe right in the chat. Chat channel. Okay, so yeah, the silly conjecture is just this. Sorry for not making that clear. Saying the average abundance of a uniform random element of the ground set with respect to a union enclosed family is at least a half. And then by averaging, that would immediately imply the union enclosed conjecture if it were true, but of course it's not true. So, okay, for the special case of transitive symmetric union enclosed families, the special case of the silly conjecture is in fact equivalent to the union enclosed conjecture for the special case of transitive symmetric union enclosed families. So let me just, to be completely clear, what transitive symmetric means. It's transitive symmetric if, or just symmetric if its automorphism group is a transitive subgroup of Sn. And this basically means that all the points look the same. That's sort of symmetric with respect to one another. Well, symmetric, yeah. Okay, so for transitive symmetric union enclosed families, proving the union enclosed conjecture in that case boils down to proving the silly conjecture, proving that the average size of the set in the transitive symmetric union enclosed family has size at least 1 over 2. I'm going to abbreviate transitive symmetric to just symmetric. So what we really want to do is to prove a stronger average set size theorem than Reimer's theorem in the special case where the family is symmetric. Average size of the set at least 1 over 2. Okay, so this was raised in the polymath project on the union enclosed conjecture. Not surprisingly, between 2015 and 2016, Tim Gowers convened a very nice polymath project on the union enclosed conjecture. Unfortunately, it didn't prove the union enclosed conjecture, but certainly lots of things were ruled out, which is very helpful, and various conjectures were made, stronger conjectures that were then wrecked over over a period of a few months, and it was generally a very nice resource if you want to get into the linear enclosed conjecture. So the Polymorph project didn't manage to solve this special case. And it didn't, or it also, so an even specialer case, if you like, was posed, which also it didn't manage to solve, which is the case where we have where the ground set is a cyclic group of order n. It can be viewed as a cyclic group of order n, and we're looking at a very special transitive symmetric union enclosed family, which is simply the union enclosed family generated by all the cyclic translates of a fixed set. So that's that R be some fixed subset of the cyclic group of n elements, non-empty, and let's consider the union enclosed family. Generated all the cyclic translates of R, then the linear enclosed conjecture, and therefore the average set size rephrasing that I wrote up there, which I'm going to call star, holds for that union enclosed family, which I'm going to call F. Okay, so that's a much weaker, but still turns out not completely trivial conjecture. Now, of course, a bit of terminology. If G is some family of subsets of 1 up to n, we let the family generated by G just be the smallest union closed family containing that family, or equivalently, the union closed family you get by sort of taking the closure of G under arbitrary unions, or just taking all possible unions of sets in G. Union closed family, or UCF, generated by G. Okay, so this union closed family I'm considering is simply family generated by the collection of all translates of R by some fixed element of Zn, so collection of all R plus J, such that J is an element of the cyclic group order n, and yeah, I'm identifying the 1 up to n with the cyclic group of order n, so I can say it's a subset of the power set of Cn. Okay, so that special case, as far as I'm aware, was not solved during the Polymorph project. at least nobody participating in the polymath project was aware of any solution that was come up with during the polymath project. But basically, the results. One of the results I want to talk about is a short proof of that. Joint, of course, as I said, with Imre and James, and in fact, we proved something slightly stronger. Yeah. Failure of alphabetical order. Yeah. So the double primed conjecture holds. In fact, we proved something slightly stronger. Prove that if G is an abelian group, finite abelian group, and R is some fixed non-empty subset of G, then the linear enclosed conjecture holds for the symmetric family generated by all the translates of R. Of course, I mean by elements of the group. And of course, this can be written by, well, this can be written as all sets of the form, what notation shall I use? R plus X, I think, or X plus R, probably more convenient for later. Right, so that's the generating family, and so the union enclosed family can be written succinctly as just some family generated from that. So saying the union enclosed conjecture holds for that family because it's symmetric is of course the same as saying that this average set size theorem holds for it. So that's in fact what we're going to prove directly, that the average set size theorem holds for it. Okay. So it's quite a short bijective proof, although I hesitate to use the word bijective proof, but it kind of is a bijective proof. The strategy is to construct a bijection G from F to itself, such that size of S plus size of G applied to S is at least n for every set in F. And then actually that suffices, because we can just average over the union closed family F by applying the bijection and then averaging. It's a very short exercise to check that. Maybe I'll write it out right at the end if we have time. But at the moment I'll just say it's very easy to check. Okay. Now, what is the bijection going to be? Well, here we're kind of inspired by a very special case of the theorem, which is where the finite abelian group is the discrete cube 0, 1 to the n, and where the set R is just generated by all of the unit vectors in Z2 to the n, if you like. And then the translates of R by elements of G in this very special case are purely all of the Hamming balls. So unions of those are precisely neighborhoods of arbitrary sets. So we're really, in this very special case, in the business of constructing a bijection from the set of all neighborhoods of sets in the discrete cube to the set of all neighborhoods of sets in the discrete cube, such that this size condition holds, that the size of a neighborhood plus the size of the bijection applied to the neighborhood is at least n. So what would be the natural way to do that? Well, one first guess, which you first think is not going to work and then actually does turn out to work, is that you just take a neighborhood and you define G by letting G of that neighborhood be the complement of its interior, and in fact, although that's not injective on arbitrary sets, it is injective on neighborhoods, which is rather fortunate. And so and it is actually a bijection that ticks all the boxes for our purposes in the special case. So let's write that down. Yeah.
So David, I have a question. I think I'm probably missing something here.
Yeah, sure.
I mean, if R is all the unit vectors, then your set system is going to be all of the vectors that are not the all zero vector, right? So why do you say it's all neighborhoods of sets?
It's well, so R you have to think of as a Hamming ball, right? Are we agreed on that?
Sure. So R is a Hamming ball or Hamming sphere, I guess, already so one, yeah.
Right. So F is all unions of Hamming balls, right? Now, what is a union of a Hamming ball? Precisely, what is the unions? What is a union of Hamming balls? Well, it's precisely the neighborhood of an arbitrary set, right?
I think it's just a different way of view.
Maybe I think I should have included 0. Actually, I'm sorry. Yeah. No, you're right. That this was actually misleading. Yeah, I meant to. Well, not misleading, but wrong. Yeah, I should have chucked in the element 0. Sorry about that. Right, that's better. Okay, so this is a very special case, but actually, yeah. So I should just point out that obviously it does satisfy this this size condition outlined in green. Because obviously, if I have a set S, then its interior will be a subset of it, and therefore the complement of its interior, well, the size of that plus the size of the original set will have to be at least n. So certainly that is okay. So now let's see what we do in general. Well, the obvious generalization of that doesn't quite work. It's quite useful to rewrite this, actually, this F, this union closed family F. If you think about what this union closed family is in terms of some sets, it's simply equal to the set of all some sets of the form A plus R, where A is an arbitrary subset of G. And how do we define the function? Well, it turns out that the thing below almost works, but not quite. We have to add on. We have to take the negative of that in general. Of course, with z2 to the n, it makes no difference because every element of that Abelian group has order 2. But let me take g of s to be minus the complement of the interior. Of course, we have to define interior correctly in order for this to work. And the complement is just, of course, G minus it. So Now here, the interior is a special interior with respect to the set R, which in turn is with respect to the set G. So we need to define, we need to choose the right notion of interior, and it turns out if you try as hard as you can to generalize that sort of baby proof below to the slightly more general case above, then the right generalization kind of pops out, and we define the interior of a set S with respect to the fixed set R, which is fixed for all time, to be all of the elements in G such that if you plus any element of our fixed set R to that element X, we remain, well, we are within the set S. So there's a slight annoyance in the general case that the interior need not be a subset of S, but it actually it actually still works. If R contains the zero, the zero of the abelian group, which we can actually assume will log, at least in the cyclic case, it's very easy to see that. Then in fact the interior is contained in S, but in general not necessarily. But that actually doesn't cause any problems for us. And actually, so it's clear. It's basically clear that so since for any fixed element of our fixed set R, the map there X maps to X minus R0 is an injection from the set's interior to itself. It follows that the size condition in green automatically holds. Yeah. What else do we need to check? We need to check that it's an injection, and it's fairly easy to check. That G, when we restrict it to F, is an injection on F. Of course, we can define G if we like on the whole of the power set of the group, but and if we do, then it's not an injection on the whole power set of the group, but it is an injection when we restrict to F, much as when we restricted our previous Troy G down here to neighborhoods, it was an injection. And probably the easiest way of checking that is to rewrite the definition of G, in fact. We can actually say that it's equal to minus the complement of S plus R, and then it's pretty easy to check that it's an injection. Actually, I think I'll check it in a different way. So, apologies. So, so this follows from the fact that if we define the neighborhood of a set with respect to R, which I'm going to write NR of S to be simply the sum set of S with R. Which, if you think about it, corresponds to the humming ball example. When R is basically a humming ball, this is the ordinary neighborhood of a second discrete cube. So it's a slightly weird looking definition, it just makes sense. So neighborhood of S with respect to R. So we've kind of defined the R interior, if you like, the R neighborhood, and as in the as in the toy example, it turns out that the neighborhood of the interior of a set is precisely the set if that set is a neighborhood. So so the neighborhood of the interior of a neighborhood is the original neighborhood. So it's very injective. The last thing we have to check, because the size condition is trivial, the last thing we have to check is that it actually lands in F, which is not completely clear from the definition of G. And for that, it's helpful to rephrase the definition of G very slightly. So we must check that the image of curly F under F is contained within F. Then when we restrict G to curly F, it will indeed be a bijection from F to itself. And that is a simple exercise that I think I'll have to leave for the interested reader. So I see that I can't quite see that bottom line, so I'll have to write up here. I'm very, very nearly finished. I'm supposed to leave 5 minutes for questions, but very nearly done. In fact, it's pretty easy to check that G of S can be rewritten as I wrote before, minus the complement of S plus R. Okay, so all right, end of sketch proof. Because although I haven't quite dotted all the I's and crossed the T's, I'm sure any of you can do that if you take the time. So I should say that after we posted this online, this short note thingy, someone did get in touch with us and say that there's a paper written by Johnson and Vaughan in 1998, and they didn't quite prove this, but they constructed a bijection which in many cases is the same as ours, not all cases, but in many cases. In fact, you can do some quotienting argument with abelian groups so as to reduce our case to their case. Ours looks a bit more general, but in fact, after this quotienting argument, it isn't more general. And then if you add in the empty set, which for some annoying reason they left out, annoying for our purposes, then you can kind of tweak their proof to get our result. But that kind of that requires several pages. So and this, if you do it more economically than I have, is basically almost a 5-line proof, or perhaps even less if you use a long definition of a line. So we thought it was worth just presenting this succinct proof. And of course, the natural open problem is, well, A, solve the union closed conjecture, B, maybe a bit more ambitious than our small contribution, but maybe more feasible than the entire union closed conjecture, is to prove it for transitive symmetric sets. So I'll stop there, and thanks very much.
Thank you very much, David. Could I ask the audience to unmute themselves and thank David, please? Are there any questions?
I have a question. David, the internet cut out on me briefly when you were doing the silly conjecture. So you might have answered this already. But the silly conjecture was that the average size of a set in a union closed family was at least n over 2. Is that right?
Yes, that's true.
And I saw on your slide an example where the set family consisted of the empty set, the set 1, the set 1, 2, the set 1, 2, 3, etc.
Yeah, it was a very silly counterexample, but it is a counterexample.
But I don't understand the counterexample. It looks like that does have average size n over 2.
Well, so there's one set of size n, right? There's one set of size 0, there's one set of size 1, and there's one set of size 2. Now just take n to be very, 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 very large.
I think, Peter, you saw dots. No dots.
I thought I saw the dots and I thought it meant, I got it. Okay.
Oh no, yeah, you thought it meant the whole chain. Oh dear, sorry. I hope I didn't put dots, but I certainly didn't mean to put dots.
Oh, I see. Okay, so it's 1, 2, 3 was not there.
Yeah, 1, 2, 3 would not be good.
I got it. Okay, that makes sense.
To be at least 4.
Yeah, and so presumably part of the silly conjecture was that you do require the full universe to be one of the sets in the family. Otherwise, it would be even sillier.
Well, yes. Okay. Yes, that's true. I mean, you can also, I mean, yeah, you can also demand that union closed families sort of separate points. That's often what researchers on this do, and that means you can't quite use my silly counterexample, but you can easily cook up other examples that do separate points. And in fact, the Polymer project posed a variant of the silly conjecture, which is that if you take a uniform random non-empty set in the union closed family, and then you take a uniform random element of that non-empty set, then the abundance of the thing you get at the end has expectation at least a half. And that also turned out to be false. It was wrecked, I think, by Tom Bloom using an example with a 10-element set. But of course, it was still interesting to work out whether it might hold up to an absolute positive constant, because that would obviously, if it were true, imply the union closed conjecture up to absolute positive constant, which would be amazing. Unfortunately, it was also the variant of the silly conjecture was also false up to an absolute constant. Yeah, that's something I pointed out on the Polymer project. But
Good, that answers my question, and thanks for that lovely proof that you showed us.
well, yeah, a lot of the credit obviously goes to Imre and James. But yeah, thanks for the invitation. It's nice to have something that you can almost present in full in a 1-hour seminar.
Are there any more questions? So maybe I have one. So your proof is when you have one generator. Now, suppose you have 2 generators in your group, then of course you get this conjecture up to a constant 2. So like I could find an element which would be included in quarter of the sets.
Yes.
So could you beat this quarter? Could you do 0.26?
We didn't try that actually, but we did try to prove it for 2 generators, the whole average set size theorem for sets generated by an R and an R primed, and we failed. It seems quite a sensitive proof to that kind of thing. But yeah, no, that's also a very nice natural question to, what can you get with with the union closed family generated by all translates of R and all translates of R primed. Of course, we'd like to prove it for translates of an arbitrary fixed finite number of sets, but yeah, two is a natural place to start. So yeah, no, the answer is we didn't actually think about improving the obvious 1/4 bound, but that is a nice starting point. Yeah.
Thanks.